Good evening, everybody. This is Sriram Bhyravarapu, a postdoc at the Institute of Mathematical Sciences, Chennai. So in this short talk, I plan to mention the results of my recently accepted paper at IVOCA 2021. The title of the paper is Conflict-Free Coloring, Graphs of Bounded Clique Width and Intersection Graphs. It is my joint work with Tim Hartmann, Subrahmanyam, Kalyanasundaram, and Vinod Reddy. Let's get started. As the title suggests, it's a coloring problem. Graph coloring is an assignment of colors to the vertices of the graph such that adjacent vertices do not receive the same color. Conflict-free coloring is also an assignment of colors to a subset of vertices of the graph such that for every vertex there is a uniquely colored neighbor or distinctly colored neighbor. Let us see this with an example. Consider the graph and the coloring given. The vertices 1 and 2 are colored. The vertices 3, 4, 5 are uncolored. The vertex 1 has a vertex 2 which is distinctly colored among all its neighbors. Similarly, the vertex 2 has the vertex 1 which is distinctly colored among all its neighbors. Vertex 3 has the vertex 1. Vertices 4 and 5 have the vertex 2 as the distinctly colored neighbor. Since every vertex has a distinctly colored neighbor in this graph, we say that this coloring is a valid conflict-free color. So what about an edge? We give the same coloring as we have given above. The vertex 1 has the vertex 2 and the vertex 2 has the vertex 1 as a uniquely colored neighbor. So this conflict-free coloring need not be a proper coloring, meaning adjacent vertices can share the same color. So here the vertex 1 has the vertex 2 as the uniquely colored neighbor. Vertex 2 has only one vertex which is colored. So the vertex 1 acts as the uniquely colored neighbor for vertex 2. Vertex 3 has the vertex 1 as a uniquely colored neighbor. Vertices 4 and 5 as before have the uniquely colored neighbor 2. So the vertex 1 has the vertex 2, vertex 2 has the vertex 1 in this case as well. Formally, given a graph G, a conflict-free coloring is an assignment of colors to a subset of vertices such that every vertex has a uniquely colored vertex in its neighborhood. By uniquely colored vertex, we mean the neighbor, one of its neighbors should be distinctly colored. The minimum number of colors required for such a coloring is called the conflict-free chromatic number. So since we're talking about the neighborhoods, both the open neighborhoods and the closed neighborhoods version of the problem have been studied. So they are called CF-ON star coloring and CF-CN star coloring. This problem was first introduced by Ivan Lotka, Ron and Smorodansky in 2004, motivated by the frequency assignment problem. It has been widely studied in both the open and closed neighborhoods. It was shown that root and many colors are actually sufficient and necessary for a CF-ON star coloring, and log square and colors are sufficient and necessary sometimes for a CF-CN star coloring. People have also studied the problem on various geometric intersection graphs like disks, squares, rectangles, interval graphs, etc. Most of the variants of this problem are NP complete. Coming to the results of this paper, we first show that the problem is FPT with the combined parameters clique width and the solution size, where the solution size is a number of colors k. We then study the problem on graphs of bounded clique width, which includes block graphs and co-graphs. Block graphs have clique width at most 3 and co-graphs have clique width exactly 2. We show that 3 colors are actually sufficient to CF-ON star color a block graph and 2 colors are actually sufficient to CF-ON star color a co-graph. So since block graphs and co-graphs have constant clique width and their upper bounds are constant, so our FPT result implies a polynomial time algorithm for both block graphs and co-graphs. For interval graphs, we show that 3 colors are actually sufficient, and we also come up with an tight example where 3 colors are actually necessary. For proper interval graphs, we show that 2 colors are sufficient. For unit square and unit disk graph, we show that 27 colors and 76 colors are actually sufficient, respectively. For Neisser graphs, we show that k+1 colors are actually sufficient and sometimes necessary. On split graphs, we show that the problem is NP complete. So, and this is the current status of the problem, where after submission to IVOCA, we studied the problem on both unit square and unit disk. We showed that both the problems are NP complete. So one open question in this work is to improve these upper bounds from 27 to maybe a single digit, or and also 76 to a single digit. Yeah, so this is all I have to say. If you have any questions, we will meet during the conference. Thank you.